Hello, my name is David Jeffs, and I worked with Sean McDonald on our AI project. Our project involved comparing search algorithms versus genetic algorithms. The goal of the project was to use a Pac-Man maze solver from the University of California, Berkeley, to test out various algorithms for solving a maze using the very classic Pac-Man background. We originally had a goal of generating random maze levels to use. The search algorithms that we used were A star and the depth first search algorithms. And then we also created a genetic algorithm that would find a path through the maze. And then we compared all of them in terms of number of operations taken, time, and efficiency. The greedy best first search worked really well and scaled very well and was very fast, but it didn't guarantee the best path. And poor implementation can lead to infinite branching because sometimes it would choose the wrong path and then continuously follow down that path and not actually be able to find its way back to a path that would finish. Here's a demo of the path, if it'll load. So here you can see the Pac-Man started in the bottom right corner. The darkest red path is the path that has been searched the most often. All parts of the maze that have been highlighted show paths that have been searched. And the darker red paths shows the ones that have been searched the most times. The light gray is the paths that were searched the least. The A-star search guaranteed the shortest path every single time. However, it took a little bit longer to work and did not scale particularly well. And so here's a demo of that. Again, you're starting in the bottom right corner with the Pac-Man. And so here you can see it followed the exact same path as the greedy best first search, except if you look at the total map, it searched many more nodes than the greedy best first search. The genetic algorithm also scaled very well. However, it was very time consuming to run, very difficult to implement, and took an absurdly long amount of time to find a correct path. And with the computing limits of my computer, I was not able to give it enough time to find a solution. But here's a demo of it in GIF form. So you can see it's starting in the bottom right corner, and it's kind of just wandering around trying to find a path, though it is unsuccessful. And as you can see in the example on the bottom that I have listed, it searched over 10 million nodes, and the path that it had is 302 moves long, and was found in generation 184 out of 250. So this run was using 250 generations. The genetic algorithm started with a path length of 300 and built from there. As you can see, it only used a path of 302, so it only added 2 nodes. And in this case, was not able to find the path. With some of the smaller mazes we tried, it was able to find a path, but there were some issues with the Pac-Man framework that we built this off of that caused it to slow down a lot when there was successful paths, because it had a successful path but was continuing to search even though it already had found one. And that's it. Let me know if you have any questions. The code is all online too for you to run. It all works. If you use some of the smaller mazes, I'd recommend decreasing the original path size that the chromosomes are generated with, and the number of generations can also probably be decreased because you won't need as many generations to find a correct path. Some lessons that I learned are that genetic algorithms are very hard to implement, and they take a very long time to implement. With this problem, I had some issues at first trying to fit it into the Python framework, but I was able to. And if I were to do this again, I'd set it up so that the genetic algorithm generated a correct path first, and then from there optimized that path, instead of trying to find a path while optimizing it at the same time. Thank you, and have a great day and summer. Hello, my name is David Jeffs, and I worked with Sean McDonald first, and then from there optimize that path, instead of trying to find a path while optimizing it at the same time. Thank you, and have a great day and summer.